kinematics with variable acceleration using calculus. The gradient of a velocity time graph gives acceleration, and in this example we can see we have a straight line graph. The gradient is the same at every point because it's a straight line, so we have constant acceleration, so we can use Suvat formulae for problem solving. The area under the graph will give displacement or distance traveled. In this graph we can see that the gradient keeps on changing. We have a curve, so the acceleration is not a constant, so we cannot use Suvat formulae anymore. Now we have to use calculus, and the acceleration is given by dv by dt. So if a velocity function is given with respect to time, then we differentiate to get the acceleration. Our acceleration is variable. The area shaded is given by integration, so we take the velocity function and integrate with respect to time. The distance traveled is the sum of these two areas. We need a positive area for B, a positive area for A, you add them together. If we're looking for displacement, then it's the area of A minus the area of B, where the area of B is a positive area. So as an example, if A is 5 and the area of B is 7, the distance traveled is 12, so that could be in meters, 12 meters, and the displacement would be 5 minus 7, so the displacement would be minus 2 meters. Okay, so starting with a function for displacement, that will be a function in time. For displacement we differentiate, so dx by dt gives us the velocity function, and then we differentiate the velocity function to get the acceleration function. Now because we took the displacement function, we differentiate once, twice. This is an alternative notation for acceleration, the second derivative of displacement. Now starting from acceleration we can go back to velocity, and from velocity we can go back to displacement, but we integrate. A summary of the previous diagram. Example 1. We have a function representing displacement. We want to find the velocity at t equals 3. So at the moment we're here and we want to go to velocity, so we need to differentiate. Okay, so we differentiate dx by dt. This is now the velocity function, and then we substitute in t equals 3, so the velocity is 76 meters per second at t equals 3. At what time will the object come to rest? So when is the velocity equal to 0? So we have our velocity function, and we know it's 0 for rest. We solve, t is equal to 2 seconds. Find the acceleration when t equals 1.5. So we start with our velocity function and we have to differentiate to work out the acceleration. Velocity function dv by dt will give us the acceleration. T equals 1.5, we substitute that in here, so 27 meters per second squared. And because the acceleration is variable, this acceleration is only for that value of t. As soon as the value of t changes, so will the acceleration. For practice, have a go at these questions.